So here's the solution to 26b. We have the situation where the projectile is fired at some angle. It has its speed of 180 meters per second and it needs to go a distance of 75 meters, and we need to find the angle. So I started over here with the vertical motion. So we have a 1/2 at squared plus initial velocity times time plus initial position. So there should be a 0 here. V sub y means the initial velocity in the vertical direction. Solving this, we would factor out a t and get two solutions, one of which is t equals 0. The other is t equals v sub y divided by 4.9. So that's the value of time out here. And then relating that to the horizontal motion. So horizontal motion, the horizontal distance is the range, which is 75, and that's going to be the velocity times time. So solving for t gives us this. Equating these two values for t gives us this. And then bringing in the more complicated aspect, v sub y is going to be, when we do a triangle up here, 180 times the sine of theta. That's where this comes from. I cross multiplied, so v sub x is the horizontal component of motion, which is 180 times cosine of theta. That's where this comes from. And then cross multiplying here, we have 4.9 times 75, the range. Dividing by 180 and 180 gives us this. This is a trigonometric identity. So sine theta, cos theta, I'm taking this and putting it here and setting it equal to this, multiplying by 2, and then taking the inverse sine and then dividing by 2 to deal with that. So that gives us this. This is degrees. I should have written that here for our angle. Now this was the approximation that we basically left off with in class. Phil had solved for this on his own, where we calculated, if it had been shot straight, the distance that it had fallen, which ended up being this. So this was our value for time it takes to go this distance horizontally, negative 1/2 at squared plus v sub I t, which is 0, plus the initial position, which is 0. So this value, which was this many meters, is how far it falls. So I left it in this form so there was no rounding involved. This is the opposite side, meaning this. This is the horizontal side, I'm recording, meaning this. And then we're going to do the inverse tangent of this over this. So the amount it drops by the horizontal distance it goes, giving us this angle. So this is good. The two answers are very close. The actual value is slightly more than the approximation, and the reason is because when it's shot at this angle, the horizontal component of motion is actually slightly slower, so it takes slightly more time to get to here, meaning it needs to be fired at a slightly higher angle. So we see this is slightly larger.